Hello students, we now begin our next chapter on chemical reactions and stoichiometry. Wheels, beds, handles, axles. What does this have to do with chemical reactions? We shall see. We shall see that the process of assembling a wagon from its components is very much like the way we produce products in chemical reactions by having different reactants come together, changing the way the atoms are bonded to one another to arrive at products. And the important considerations that we'll have in this chapter is about the stoichiometry of these reactions and how we can use stoichiometric relationships to determine the amount of product produced, the amount of limiting reagents, etc. At the bottom I show a typical chemical reaction. Methane plus 2 oxygen molecules going to carbon dioxide and 2 waters. The first thing we need to do is to talk about various types of chemical reactions. And I'm going to try to systematize this discussion. So first of all, we can talk about chemical reactions of various elements or various compounds with oxygen, reactions with oxygen. Almost every element, whether it's a metal or non-metal, will react with oxygen. For example, to form iron 2 oxide or iron 3 oxide or carbon monoxide or carbon dioxide or nitrogen oxide, nitrogen dioxide, etc., sulfur dioxide, silicon dioxide, common sand. Organic compounds react with oxygen in what we can call a combustion reaction. For example, C3H8, which is propane, can react with oxygen gas to form carbon dioxide gas and water. So this is one general type of chemical reaction of any of the elements or compounds with oxygen. We can also have what are called combination reactions, which it can also be called composition reactions, in which we take 2 or more substances, react them together to form a product. For example, we can have a reaction of 3 magnesiums with 1 diatomic nitrogen to form magnesium nitride. This particular kind of reaction, in which only elements react together to form a compound, can also be called a formation reaction. So the second type of general reaction is a combination reaction, forming a product molecule by reacting smaller components or elements together. The reverse of that is something we can call a decomposition reaction, in which we break a substance up into smaller parts. For example, mercury 2 oxide, if we heat it up, and the little delta is sort of a universal sign that we'll use for heat it up, add thermal energy. For example, if you heat up mercury 2 oxide, and the little delta is this sign for add thermal energy, if you heat up mercury 2 oxide, you can decompose it or break it up into its elemental components of 2Hg and oxygen. Another example would be taking calcium carbonate, chalk, heating it up and decomposing it to calcium oxide and carbon dioxide gas. That is essentially converting limestone to lime. A third type of general chemical reaction is what we could call an exchange reaction. And in general, we mean something like this. Ionic compound AX, where A is the cation, X is the anion, can react with a second ionic compound BY, B being a second cation, Y being a second anion, to essentially switch partners to form AYBX. I sometimes analogize this as 2 ionic compounds going to a dance. And after they go to the dance, they switch partners and dance. These ionic compounds can have exciting social lives. Anyway, exchange reactions are those in which essentially the cations and anions switch partners. And then we see if any particular kind of reaction occurs. For example, this could be an acid-base reaction, or it could be a precipitation reaction, or an oxidation-reduction reaction. I note that exchange reactions oftentimes occur in aqueous solutions. Before going further, we need to introduce the concept of electrolytes. Electrolytes are those species which, when present in aqueous solution, will increase the conductivity, the electrical conductivity of the aqueous solution. That is, electrolytes are ionic compounds that facilitate the conduction of electrical current through water. For example, sodium chloride, which when you dissolve it in water, the cation and the anion dissociate from one another, forming sodium cation. The little AQ subscript means hydrated or dissolved in water, and chloride anion, again with a little subscript AQ, meaning dissolved in water or hydrated by the solvent water molecules. And the cations and anions can then conduct electricity by diffusing around separately from one another in the solution. And if two electrodes, positive electrode and a negative electrode, are inserted into the solution and a voltage source is applied, the cations will diffuse towards the cathode and the anions will diffuse towards the anode. Strong electrolytes are those ionic compounds that will completely, or almost completely, dissociate to form cationic and anionic species that diffuse separately from one another. Whereas weak electrolytes are those compounds that only partially dissociate into the separate cation and anionic species. A little later, perhaps in the second semester, we'll talk about weak acids and how they only partially dissociate into a cationic form, which was actually, in those cases, will be the proton, H plus hydronium ion, and the corresponding anion. A non-electrolyte is a substance which, when dissolved in water, does not produce a cation and anion, and thus will not support the conduction of electric current. Examples of non-electrolytes are glucose and sucrose and urea and ethanol. I'm sure most of you have never tried dissolving ethanol in water, or have you? All right, let's go on to acid-base reactions, and this is your prototypical acid-base reaction. Hydrochloric acid, again, little AQ means it's been dissolved in aqueous solution, plus sodium hydroxide, your typical base, again dissolved in aqueous solution. If you mix a solution of hydrochloric acid with a solution of sodium hydroxide, this is a typical acid-base exchange reaction in which the cations and the anions switch partners. That is, the chloride anion from hydrochloric acid will switch partners and combine with the sodium cation of sodium hydroxide to form sodium chloride. And likewise, the H plus, what we will call hydrogen ion or hydronium ion of hydrochloric acid, will switch its anion and combine with hydroxide anion from sodium hydroxide to form water. So the transferring of a hydrogen ion from an acid, such as hydrochloric acid, to hydroxide anion of a base, such as sodium hydroxide, is what really happens when we have an acid-base reaction, thus forming water and a salt. In this case, the salt would be sodium chloride. An exchange reaction. Now, generally, you'll be able to recognize an acid, either by its name or the fact that it has a hydronium ion as its first component on the left. And usually you can recognize a base by the presence of a hydroxide ion in its chemical formula, but not always. For example, if you look at my example at the bottom, the base is actually ammonia, and you don't necessarily see the hydroxide, but as we'll learn later on, ammonia, when dissolved in water, produces hydroxide ion. It's just that it's not obvious in the chemical formula for ammonia shown here. But hydrochloric acid plus ammonia can form ammonium chloride, and this also is an acid-base reaction. A second type of exchange reactions, which you'll need to be able to recognize, are what are called precipitation reactions. But to understand and be able to predict precipitation reactions, you first need to learn the solubility guidelines. And this page has a lot of information on it, and you may want to print this and look at it for a while. But basically, you need to learn these solubility rules or guidelines, and let's step through them. They're really not as difficult as they might appear at first glance. So, if you start at the top, this is the way to interpret this little table. If you look over the left, if the cation of an ionic compound, remember cations come first and then anions, if the cation is a group 1A, that is an alkali metal, group 1A metal cation, or ammonium, NH4+, then an ionic compound involving sodium cation, for example, or ammonium cation, is always soluble, no matter what the anion is. Pretty easy rule. So if the cation comes from group 1A or is ammonium, then the ionic compound is always soluble. I like that rule. Second rule, also one that you'll like. If the anion is nitrate, nitrite, perchlorate, chlorate, chlorite, hypochlorite, or acetate, no matter what the anion is, the ionic compound will be soluble in water. Okay, so two pretty good rules. Basically, it means keep your eye peeled for sodium, potassium, lithium, ammonium, rule 1. Or the second rule, keep your eye peeled for nitrate, nitrite, chlorate, perchlorate, etc. because those ionic compounds will always be soluble in water. Okay, let's go to the next rule. If the anion is one of these three halogens, or halides, as we would call them if they are anions, chloride, bromide, or iodide, if the anion is one of these three, it will be soluble, the ionic compound will be soluble, except when the cation is silver, silver plus 1, lead plus 2, or mercury plus 1. Now, it may seem like I'm going to throw a lot of random things, but if I show at the right a little representation of the periodic table, and I show that silver cation, lead plus 2 cation, and mercury plus 1 cation are all kind of grouped together at the bottom right-hand corner of the transition metal area. Now, there are other metal cations that would be in this except for category as well, but because we don't use them in our example problems very much, let's only focus on these three exceptions. So again, if the anion is chloride, bromide, or iodine, the ionic compound will be soluble except when the cation is silver plus 1, lead plus 2, or mercury plus 1. Well, what about fluoride? Fluoride ionic compounds will be soluble except when the cation is calcium plus 2, barium plus 2, or strontium plus 2. My, how will I remember this? Well, they're all in group 2A, and a way for you to remember this is, remember, why do we put fluoride in our toothpaste? Well, we do because the fluoride forms a very insoluble ionic compound with calcium, calcium fluoride, calcium being a natural component of your teeth. So that's actually why we have fluoride in all of our toothpaste. So not only calcium fluoride is insoluble, but barium fluoride and strontium fluoride, which are all together in group 2A. So fluoride ionic compounds are generally soluble unless the cation comes from group 2A, or the bottom part of group 2A, calcium cation, barium cation, and strontium cation. All right. Next we come to sulfate, and sulfate shares the problems of both of the two above rows. That is, sulfate ionic compounds are soluble except when the metal cation comes from that bottom right-hand part of the transition metal area, silver plus 1, lead plus 2, mercury plus 1, or group 2A metal cations, calcium plus 2, barium plus 2, strontium plus 2. Or at least the bottom part of group 2A metal cations. All right, so that's the first part of these rules that you need to remember. Then we go to some others, and you have to sort of look at the bottom part of this table backwards. If the anion of an ionic compound is carbonate, sulfite, or phosphate, the salt, the ionic compound, will be insoluble unless rule 1 applies at the top. That is, unless the cation comes from group 1A metal cations or ammonium. We really didn't need to have this rule because the first rule actually applies, but because you might wonder about carbonates and sulfites and phosphates, this is how we deal with those. Also, the anion might often be hydroxide or oxide, in which case the ionic compounds will be insoluble unless, again, the first rule applies, that is, the metal cation comes from group 1A or ammonium, or the metal cation is calcium plus 2 or barium plus 2. Basically, calcium hydroxide and barium hydroxide are relatively soluble. Now, we've probably mentioned before that oxide, O-2, doesn't exist as a species dissolved in water. That still is true, and so don't get confused about this, but we're saying that oxide, O-2, ionic compounds are generally insoluble. So if you had iron oxide, it is insoluble. Okay, so the O-2 is not existing as a species in aqueous solution because it's part of an insoluble ionic compound. And lastly in this table, sulfides, S-2. S-2 salts or ionic compounds are insoluble unless, again, the first rule applies, the metal cation comes from group 1A or is ammonium, or if the metal cation comes from group 2A. So those are solubility rules. Now, they They will seem complicated when you look at them, but why do we have to know them? Well, you have to know the solubility guidelines so you can predict whether or not an exchange reaction will occur leading to an insoluble product. Let's, for example, look at the very bottom of this slide. Copper nitrate. Now, I've shown you, little AQ says that it is soluble in aqueous solution, or it's dissolved in aqueous solution. But if I had not shown that little subscript AQ, would copper 2 nitrate be a soluble ionic compound? Well, yes, because the second rule in this table says that if the anion is nitrate, then regardless of what the cation is, it's going to be soluble in water. So copper 2 nitrate is a soluble ionic compound. And I say plus ammonium sulfide. Well, again, rule 1 applies because the cation is ammonium. So regardless of the anion, this is going to be a soluble ionic compound. Okay? And of course, again, I show you the little subscript AQ, so it was a giveaway. But the question is, if you mix an aqueous solution of copper 2 nitrate and ammonium sulfide, you mix them together, and they attempt to exchange partners, will you form an insoluble ionic compound? Think about this in your mind. Switch to partner. So the copper plus 2, which starts off with the anion being nitrate, switch its anion to the other one. And likewise with ammonia, switch its anion with the other one. And you'd get something like this. You'd get copper sulfide and ammonium nitrate. Then the question is, are both of these soluble, or is one or both insoluble? Well, obviously the ammonium nitrate is soluble. In fact, it's super soluble because ammonium salts are always soluble and nitrate salts are always soluble. So ammonium nitrate is going to be really soluble. But copper 2 sulfide is not soluble because if you look at the very bottom guideline or very bottom rule, sulfide salts are insoluble unless, but copper is not in that unless list. So this would be a precipitation reaction. If you mix these two soluble ionic compounds together, copper 2 nitrate and ammonium sulfide, you would form an insoluble copper sulfide precipitate. The third possible type of exchange reactions are what we call oxidation-reduction reactions. In this case, the switch, the transfer, is actually transfer of electrons from one reactant to another. Now, you've probably heard the mnemonic, loss of electrons is oxidation, LEO, loss of electrons is oxidation, and gain of electrons is reduction, GER, gain of electrons is reduction, right? That's a good way to remember what's happening. What I show is a prototypical oxidation-reduction reaction. A solution that contains copper plus 2, cation, can react with another solution that has zinc, the metal zinc in the solution. It's not dissolved necessarily. That's what the subscript S means. But if I mix two solutions together, one that has copper plus 2 dissolved and one which has a piece of zinc metal, an oxidation-reduction reaction will occur in which the copper plus 2 gains 2 electrons to form copper metal, which will be a solid. So copper plus 2 gains electrons, and zinc can lose 2 electrons to form zinc plus 2. So again, remember, when a substance loses electrons, we say it becomes oxidized. Zinc becomes oxidized from zinc to zinc plus 2. Copper plus 2 gains electrons and becomes reduced. All right, how am I going to keep up with this? Well, to keep up with this, you have to know oxidation numbers, and you have to be able to quickly look at a substance and determine what the oxidation number is of the various elements in the substance. Oxidation numbers are quick and dirty estimates of the charge on individual atoms of a molecule or a polyatomic ion. Now, when I say quick and dirty, I'll explain that in a moment. So here are the rules for determining the oxidation number of any species. You essentially follow these guidelines in this order. First rule, the sum of the oxidation numbers must be equal to the charge on the species. So if it's a neutral molecule, the sum of the oxidation numbers has to be 0. If it's an If it's a negatively 2 charged anion, the sum of the oxidation numbers has to be -2. Second rule. Group 1A metal cations have oxidation number +1. I bet that's not difficult. That means like sodium, if it's in a molecule, sodium cation will have an oxidation number of +1. Group 2A metal cations in an ionic compound will have oxidation number of +2. That means something like calcium in an ionic compound would be calcium +2. And that's what you thought it was going to be because it's in group 2A. The next rule is fluorine in an ionic compound will always have an oxidation number of -1. That's probably what you thought it was going to be. Oxygen is usually -2 in a molecule, but it can be -1 if it happens to be in a peroxide. That means you have to keep your eyes peeled for any O2 species, O2 -2 species. Hydrogen, this is another one where you notice the word usually. Hydrogen is usually +1, but it can be -1. And then we get to chlorine, bromine, iodine, are usually -1, which is what you might have guessed, but they can be +1, +3, +5, +7. Oh my. And I forgot to mention, so let's go back and look at a little box. The zeroth law, the very first law, or the law before law number 1, is that if you're talking about an element, something on the periodic table, the oxidation number is 0. So for diatomic nitrogen, oxidation number of the nitrogen is 0. For diatomic fluorine, 0, because that's the element. For sodium metal, oxidation number of the sodium is 0. So the other rules that we've just listed apply when you're talking about a molecule or a polyatomic anion or cation. Now let's take an example. Let's work an example. Let's consider chlorate, ClO3 -1. Let's determine the oxidation number of the chlorine and the oxygens in this polyatomic species. So basically, we follow the rules down the list, and I'll oftentimes say, we start with what we know or think we know and go to what we are less sure about. And that's basically the order of these guidelines. So the total charge on this species is -1, which means that the sum of the oxidation numbers has to be equal to -1. Now between chlorine and oxygen, which one do we feel most comfortable taking a stab at in predicting its oxidation number? Well, again, if you go down this list, the first rule that applies is oxygen is usually -2. We have more confidence in assigning oxygen a -2 than assigning an oxidation number to chlorine, because we saw at the very bottom, chlorine can be a lot of things. So if we say that oxygen is -2, and there are 3 of them, 3 -2s, it's -6. The total charge on chlorate has to be -1, so the charge on the chlorine has to be +5. Yes, that's the way we assign oxidation numbers. We start with what we know or think we know, and then work towards what we have less confidence in, realizing that the sum of the oxidation number has to be equal to the charge on either the molecule, which is 0, or the polyatomic anion or cation. Now, in this, we predicted, by this what I call quick and dirty estimate of the charge on each atom in chlorate, that chlorine would be +5 and oxygen would be -2 in its charges. If we have talked about Lewis structures and formal charges, you can also now quickly determine the formal charge on the oxygen and chlorine of chlorate after drawing its Lewis structure. You want to take a second and do that? Yeah. Well, the chlorine would be in the middle because it's the least electronegative, and you'd have 3 oxygens. You distribute all of the valence electrons, and you would come up with a Lewis dot structure. And when you then slice the bonds and let the electrons snap back and determine the formal charge on each of the atoms, you would find that the 3 oxygens would be -1, and the central atom, the chlorine, would be +3. So the formal charge methodology leads to a way to determine the charge on atoms in a species. And these oxidation numbers are a second way of determining the charge on atoms in a species. Which one is most reliable? Well, actually, the formal charge method is more reliable and gives a better estimate, but it takes more time because you have to draw out the Lewis structure. And sometimes you'll have to evaluate resonance forms, etc. Whereas these oxidation number guidelines or rules are that quick and dirty way to estimate the charge of each atom in a species. That's what I mean by quick and dirty. And why do we resort to quick and dirty? Because we want to move fast, because we're looking at reactions and we want to determine if an oxidation reduction process has taken place. Basically, that means, has something become oxidized and has something become reduced in a reaction? Are the oxidation numbers changing between the reactants and the products? Okay, now, as practice, this is my suggestion. Take lithium oxide, phosphoric acid, phosphorus trifluoride, permanganate, dichromate, hydrogen sulfide, sulfite, perchlorate. These are just good ones to work with, and determine the oxidation number on each atom in the species. And if you want to compare one or two with the formal charge, that might be useful for you as review. Now, why do we want to do this again? Because if we have a reaction such as I've shown, zinc 2 oxide plus carbon going to carbon monoxide and zinc, the question that you will be asked is, how do you describe this reaction? What type of reaction is this? Is this an acid-base reaction? I don't see anything that I would call an acid, and I don't see anything I would call a base, and I'm not forming a salt and water as my products. Probably not an acid-base reaction. Would I call this a precipitation reaction? That is, do we switch partners in some way so that things were all soluble on the reactant side and they form at least one insoluble product on the product side? Well, no, that doesn't seem to apply either, because on the reactant side I have two things that are insoluble. That's what the S means, solid. And on the product side, one of them is a gas and the other is still a solid. So it doesn't look like this should be described as a precipitation reaction. And also, this reaction can occur even in the absence of the solvent water. But we then check as to whether or not there's a change in the oxidation number of the elements on the reactant side and the product side. And when we do that, we'll say bingo. Look at zinc oxide. The oxygen is usually -2, right? And the zinc would then have an oxidation number of +2. Very reasonable. And look at the product side. On the product side, zinc is the element, so we'll have an oxidation number of 0. So zinc goes from +2 on the reactant side to 0 on the product side. Its oxidation number has gone down. It has been reduced. Okay? If we look at carbon, carbon on the reactant side is the element, so it has oxidation number 0. On the product side, in carbon monoxide, again, if we do this quick and dirty estimation of the charges on the atoms, we say, well, oxygen is probably -2. That means that the carbon in carbon monoxide is probably +2. Okay, so carbon goes from 0 on the reactant side to +2 on the product side. It has become oxidized. Its oxidation number has increased. It's oxidized. So that's how we would recognize this as being an oxidation reduction reaction, or what we usually call a redox reaction. Notice the bottom sentence. In a redox reaction, something becomes oxidized and something becomes reduced. For at least one element, the oxidation number goes up, and at least for another element, the oxidation number goes down, becomes reduced. Okay, we've covered a lot. We're going to pause now, and when we come back, we'll move on and talk about such things as net ionic reactions, and we'll delve more into redox reactions, and we'll characterize different types of redox reactions. We'll talk about the activity series, etc. See you in a while.